Hello everyone, welcome to my workflow to create HYDROMAN character inspired from Spider-Man movie. So let's start. The very first thing is to import an interesting animation. And the goal is to create a flip simulation that is trying to stick over the body of the character during the time. But also, it needs to behave like water, so the flows of the water need to be natural. After importing the animation, this is something that I usually like to do. To freezing a frame and apply all the deformation at a rest frame. In this case, I applied a spectrum, an ocean spectrum, and a noise. This gives me a very huge control over director vision, for example. This is a noise and an ocean spectrum, but it could be literally everything. You can create custom deformation or whatever you want, whatever is in director's vision. After doing that, I take the original animation and I pass it through a point defer. I usually do this process to compute correct velocities. Usually when you do some geometry manipulation, such as clip in this case, you alter the poly count. And then when you compute the velocities, the trail node, for example, the velocities tend to go crazy and incorrect. With this point deform, you are assuring that the main topology and poly count of the geometry is preserved at rest frame and it keeps consistent during the time. So all the velocities can be computed correctly. Let's talk now about the technique I used to create this flip fluid simulation to wrap around HYDROMAN characters. So now we want to create a simulation that flows around the character, trying to mimic his shape while maintaining physical attributes somehow. So I love to use simple solutions. I love to keep things as simple as possible when trying to achieve my tasks and trying to not reinvent the wheel anymore. So I came up with an idea that actually is the ocean guiding layer that has been into Houdini by many versions. So you can create simple ocean guiding layer by clicking on the shelf if you want. And this feature is simply creating a thin layer of particles that trying to match the underwater surface. In this case, is trying to match this spectrum. So the concept is very simple, and what I wanted to try is to see if I can actually drive my particles around HYDROMAN character instead of using it just for ocean. And the first thing to do is to analyze what this setup does. If you look into DOPS folder, DOP node, or DOP network, as you want, and you can see that you have a gas guiding volume operator. this operator expects three inputs. These three inputs has been created at SOAP level. Now, what are these three inputs? Basically, if we have a quick look to this very simple graphic I did, you have the guiding surface layer that is the core of everything in this approach. This guiding surface is basically something that acts like a collider to match the ocean surface movement. And this guiding surface actually merge into collision field at DOP level. So while you're running your simulation at DOP level, this guiding surface blends with the actually collision fields. Then you have this thin layer of particles that are the particles, flip particles that are you're actually simulating. And then you have this sink layer that ensure that you have a thin layer of particles receding at the boundaries. And this is just to say, hey, I want just a thin layer of particles being simulated and not nothing under the guiding surface. And then we have the surface itself, that is the global volume that are enveloping everything, providing the boundary conditions. And we have also a guiding velocity. If we analyze how these fields are built, we can try to reconstruct them later for our specific case. The core field in this kind of simulation are a boundary vel, a boundary velocity, then we have the most important one, that is the guiding surface, a guiding sink, and then the actual surface. If we visualize all of this stuff, we can explicitly see how it looks. So we have this guiding surface that acts as a collider to drive the thin layer of particle. If we look into the flip solver in the DOP network, we can see that we are using a gas guiding volume. This gas guiding volume is expecting three inputs. The first input is the out guiding surface that is used inside. To blend itself with the actual collision field that is computed in the flip solver. So we can say easily that yes, the guided ocean surface is a collider itself. The sink layer is just providing the water level to be a thin layer of particles, and the surface itself is where the particles are scattered, and the velocity is just the boundary velocities that are trying to keep the simulation consistent based on the inputs. In our case is the spectrum. So it is creating these boundary velocities at the boundary. what we want in our case is literally to recreate these fields. So again, the boundary surface, the boundary velocity, the guiding sink, the guiding surface, to drive the simulations for our HYDROMAN. Now back to our scene. Let's start from the end, actually, where I created these custom layers. So I represented, as before, the guided surface in red. And this guiding surface is actually our ocean in the vanilla Houdini example. So this guiding surface is driving our particle layers that are represented in blue to match its motion. So this time is not ocean motion, but it's characters motion, deformation. And then the goal is then to create these layers and these fields. Let's see how I created these custom fields, these custom guided fields. And the first thing is to get our closed mesh, from which we derived a VDB surface. Second step is to take our open surface, convert it into a VDB unsigned, because we don't have here a watertight mesh, and convert fog to SDF with different expansion. So we are doing this because as first thing we want to create the sink field. In order to do that, I had to have a similar shape to subtract to from our original surface. And then the second step is to have our guiding surface field. So again, from the fog we computed here, unsigned, we convert into SDF with different expansion, and we combine with the main VDB surface. Basically, we are subtracting our guiding surface from the main surface, and then again we are combining this with the sink. So now we have our guiding surface layer by simple doing easy volume manipulations. I'm not going to go through node by node in all the parameters, because this is not a from scratch tutorial, but consider that I linked this stuff with a layer control, where I exposed a layer size parameter and a guiding thickness, and I used those two values to have a proper proportion of expansion and resolution, just to make the process procedural and quicker. Then we are going to create a velocity field. So again, we are creating a VDB volume from closed surface, where we are extrapolating the velocity attribute from the mesh, and we have that velocity field. We can visualize it easily. And then, the last but not the least, I am scattering particles from the main surface we created. This will be our thin layer of particles. that will be driven by the guiding fields. So to resume, we have our main surface from which the particles are being scattered. We have a guiding sink fields, and we have a guiding surface, and we have a velocity. So basically we replicated in a similar fashion all the fields that we saw in the vanilla Houdini guided flip simulation. Now that I have all my fields, custom fields, I can visualize them by combining in a fashion like this, where I can visualize instantly what they are doing. And with this layer control I created, I can control the thickness of guiding surface, for example, or the particle layer. See that these two parameters are related each other by affecting the proportion in these BDB manipulations. So we are just expanding and offsetting in order to maintain the main concept of the guiding fields structure. Now we want to inject this field at DOP level. So if we take this DOP network node and we dive inside, we can start feeding this gas guiding volume with the custom guided layer we created. Another quite important parameter is this stick on guide. This is basically trying to have a stick effect over the layers. So in the case of HYDROMAN is what we are looking for. We don't want that the particles have a very strong momentum, very strong home momentum. Rather, we want them to try to stick as close as possible to the surface of the character. And then we need to feed the flip solver surface volume with our boundary surface and with our velocity. The same that we ping in here. We link it here. The rest is quite standard. We need to apply, of course, boundary velocities and to apply boundary layer, because we want the particles to be reseeded when they are deleted in the sink node, but in the sink layer. Here is the result of the flip simulation. We can see that the flip particles are flowing naturally, but at the same time they are trying to stick to the guiding surface. So they are representing the character body with all its deformations, but at the same time they preserve their momentum, so they are behaving like water. So here we have splashes, here we have some interesting flows, but we are preserving the original body shape. So if we visualize the geometry, we can see that the main body of the character has been preserved during the simulation, but the flip particles are still behaving dynamically as they should. Hello guys, I hope that you liked this video and I hope this could be useful somehow during your workflow. See you soon and thanks for watching.